Welcome to the lecture on database and databases. This is a very important class. It's an important example of how we take software to help us organize our data. Okay, and so we're going to get into the topics, but first let me talk about some administrative items. So databases will be our last topic before our exam. So we've got an exam upcoming. After this lecture day, we will have one class day where we'll do an exercise on database. I'll answer any questions. We'll review for our exam, but be aware that the exam is coming up, and so please prepare for that. Ask the questions that you need in order to complete the exam successfully. The second thing is the programming project. Hopefully after our time in the lab that you've been able to finish the project or come close to that, but if you haven't, be aware that the due date for the programming project is upcoming, and make sure to get that submitted properly. All right, so here's some sample exam questions, things you should know after this lecture. Well, what is a database? What's it made up of? What is the purpose of storing things in a database? Why would we do that versus storing it in other types of files? What is an ER diagram or an entity relationship diagram? How do you draw one? What are the pieces of an ER diagram? What do they represent? And then also, what is something called data warehousing? We'll talk about that towards the end of lecture. All right, first of all, why do we care about data? Well, one of the reasons why we care about data is that it is everywhere. So this little site here, hopefully it shows up on the video, will show you in semi-real time a subset of the tweets from around the world and where they're at. They're trying to sort of randomly look at where the tweets are coming from. And so we can see all sorts of tweets. There's quite a hive of activity in North America, particularly in the United States. Looks like there's a decent amount in Mexico. Florida's got quite a bit right now. The United Kingdom, even up into Scotland, has quite a few tweets. You can see some of Spain has quite a bit. Some of the other areas of the world maybe not quite as much right now. It's probably a little time to go sleep over in some areas of the world. But there's a lot of data out there. Okay, this is just a few of many pieces of information that are being shared all the time. Okay, by 2020, that's not very far away. Cisco estimates that over 6,300 petabytes, 6.3 exabytes of information will be transferred over the internet every single day. That is a lot of cat videos. That's a lot of information. Right now, Netflix accounts for about 1/3 of all prime time, like the 5 to 9 p.m. downstream traffic. That is a crazy amount of bandwidth because there's not even that many Netflix subscribers, and already about 1/3 of our overall traffic, at least during one section of the day, is streaming video from Netflix. In 2016, on Prime Day, Amazon set their own record of averaging 636 items sold per second. Now, even accounting for multiple items per transactions, that is an insane amount of transactions and a number of items per second. And they've got to store all of that and get their systems to process all of those transactions. Similarly, on Facebook, every day there's more than 4.5 billion likes, 300 million photos uploaded, and more than 500 terabytes of data transmitted every single day already. And then on Tinder, every single day there are more than 1 billion swipes. And we've got these companies, they have to be able to store that and account for that and process that. There's just data everywhere, to the point that it's somewhat overwhelming, all right? We've even given it in the last few years a new catchword or buzzword, catchphrase buzzword, big data. And how we handle and analyze and manage big data is actually, a little bit harder than doing what, usually is called data, but now sometimes gets called small data. We have to handle it a little bit differently because it's tricky to handle so much information. Sometimes our statistical analyses that we once relied upon aren't as useful. So we've got a lot of difficulties in managing data, all right? Some of the things that are tricky is we've already talked about. There's just a ton of it out there. There's just a staggering quantity of data. Number two, the data comes from a lot of different places. Sometimes it might come from internal systems to us, like our enterprise systems. We'll talk more about these later, but our CRM systems and our supply chain management systems and our ERP systems and all of these other types of enterprise systems. But they might come from public information. A lot of companies are starting to rely on external information. For example, I've taught our healthcare IT class in the MBA program, and there's a lot of interesting healthcare information. Companies gather a ton of information on their patients, their doctors, the procedures, and so forth for billing and for patient care. But they're starting to rely on public information, things like weather and other sorts of information to help them make and run their healthcare operations, make their operations work more effectively. So our data might come from a bunch of different places, different systems. Number three, oftentimes our data is not centrally located. Now, good organizations are moving more and more towards a centrally located data where it's properly organized and properly formatted, but that isn't always the case, and that causes a challenge. Also, we've talked about the importance of information and the characteristics it has. We know that data's usefulness goes down over time. All right, recent data is on many topics more useful than old data, and so how do we deal with old data? Do we archive it? Do we delete it? Do we ignore it? How do we treat it? Okay. And then this is kind of related to multiple sources and not centrally located, but not all of our technologies communicate with each other. Sometimes we have to take something from one system to another and it doesn't talk to each other. How do we get that to work? So there's just a lot of problems and challenges in managing our data, which is why there are a ton of jobs in managing data. Now, historically, this last one, database administrator, was kind of the job for someone who's handling data, the IT job. But now we have, people who do data governance, sort of a higher level look at data and how it's managed. We have security folks, both on the database side, but also more generally. We have data warehousing professionals. We'll talk about data warehousing later. We have business intelligence and business analytics, data scientists. We'll talk more about that when we talk about those topics. People who are data architects, who know how to structure the data. We have jobs that we look just at the quality of the data and the integrity and how we maintain that and ensure that. And so the overall data management is really a management activity that involves, especially in large organizations, many different individuals and job titles. All right. So I want you to just pause for a second and think to yourself, what are the pros and cons of putting all of your data into the same file? We're talking everything, okay? Put, your schoolwork, your personal electronic files, for all of your classes, for everything, put it all in one big file. What are the pros and cons of that? See if you can think about that, and then we'll talk about it. All right, hopefully you thought about this for a little bit. Some of the pros of putting all your data in the same file is, well, it's in one place, all right? You know where everything is at. You can back it up if necessary, okay? Because it's only in one place. But if you've ever done this before, put multiple things all in one file, you'll start to realize quickly that it's a pain to keep that kind of thing organized. Even putting all of our files in one big folder is kind of a pain to keep things organized. And so it actually becomes tricky over time, especially as some information, some of our data becomes out of date. How do we know where it's at? How do we structure it and organize it? And it's really challenging. So like I said, to some extent we have the, do we put all our eggs in one basket? Well, if we do, it's easy to watch that basket, but at the same time, it's hard to keep things completely organized. Now, the other challenge is what happens if we lose the file? Well, then everything is gone. All right, let's look at some specific examples. So here's an example of some student registrations for some classes, okay? And so we'll see some of the challenges with having all of this information in a file. So we've got our students over here. We've got John and Tyrion and Arya and Peter and Daenerys and Jaime. And those of you who are Game of Thrones fans will understand the reference. All right, so let's check it out. First of all, some of the data, even for multiple students, is duplicated, right? So MIS 101, Section 7, Monday, Wednesday, 12, Wells. That's not a real section this semester. But if you look at this, why are we storing this information twice? Couldn't we just store it once? Well, the answer is yeah, we could, because we have some duplication here. And that causes a problem sometimes, because what happens if we need to change that? We need to change it now in 2 places. What if Section 7 all of a sudden needs to meet at 1:30 instead of at 12? Or what if the instructor changes? Well, that, we'd have to change it in every single location where that exists, and that's a problem. All right, next problem. Oh, well, if this is a list of my students, then it doesn't really make sense to have Jaime, who is, I guess, one of my students, but when Jamie's signed up for a criminal justice class, I don't really need to see that. So for this table here, that information is irrelevant to me. Next problem is, well, what if it's inaccurate? You'll notice that there's 2 different spellings for Lannister here. And as it turns out, this is the incorrect one that's circled. So maybe, because of the duplication here, maybe, Jaime's name was put in incorrectly once, or maybe it was changed and we only fixed it in one place. Either way, we have inaccurate data that's inconsistent with each other, and then that's a problem. Next, when we put everything all in one place, sometimes it's difficult to see the missing data. All right, in a table this small, we can see the missing data, but in some places it's challenging to see that missing data. Which course is this? Well, we could probably guess based off of some of these things, like the instructor and the time and the day, that it probably is MIS 140, but maybe it's not. Maybe there's another issue here. All right, so when we store data, one thing that database professionals do, and if you ever take a database-specific class, you'll learn quite a bit about data normalization. What that means is that we take our data and we structure it in a way in multiple tables, we'll talk more about tables in a second, to eliminate a lot of these problems. So with normalization, we're trying to minimize how much redundant or duplicate information there is, and we're trying to maximize the integrity of our data, okay, that everything is correct and up to date. Normalization also has the nice benefit of being really quite good for doing searching and querying, updating, and so it's good for processing performance, and we'll talk more about that in a little bit. In fact, normalization is optimal for almost all types of our databases. The exceptions to that is when we get to big data, sometimes, not always, but sometimes normalization isn't ideal for certain types of very large data applications. So if we're talking on the scope of Facebook and Google, sometimes no normalization doesn't work. And so we have alternatives to that, like NoSQL databases. And that's beyond the scope of this class. But also things like data warehouses. Sometimes we purposefully denormalize the data so that it's more useful for doing analytics and business intelligence, statistical analysis. And so we'll talk more about data warehouses in a minute, but kind of the point of doing those is to take it out of its normal form and make it in a form that's better for analysis. All right, so this is an important point. Here's what a database management system, sometimes just referred to as databases, this is what a database tries to minimize. We already talked about this one. Redundancy. We don't want unnecessary duplication. It just takes up space on our hard drive and it makes things slower for us to deal with. So we remove as much redundancy as possible. Number 2, we get rid of the second principle is data isolation. Now this is a tricky concept and a simple concept at the same time. Let me give you a hopefully simple example. So let's say that I have a bank account and it's got $25 in it. Let's say that I try to, there's no overdraft protection, there's no anything, I just can't remove, I can't go negative on the balance according to the bank. Let's say that I try to withdraw the $25 and my wife tries to withdraw the $25 both at the same time. The exact same time, down to the millisecond. Okay, exact same time. So we have these two concurrent transactions. What should happen? Should the bank give us both $25? Well, for my wife and I, that sounds great, right? As long as they only deduct $25 out of the account. But from the bank's perspective, they should only give one of us the $25 amount, and then take that out of our account. So with data isolation, one thing that database management systems attempt to do is they attempt to minimize isolation so that concurrent transactions actually will lead to the same result as if they were one after the other. And so there's things like locking and mechanisms behind the scenes that are beyond the scope of this class to help minimize data isolation, minimize the problems with inconsistent data that's caused by these concurrent transactions. And then the third one is, what we've already talked about also, is data inconsistency. So if I change my email in somebody's database somewhere, it should change it for their entire system, right? I shouldn't have to change it in multiple locations. Now, redundancy helps with that. Removing redundancy helps with that. But I was working, a friend of mine was working on a project, and they had to change their database password in their code. And usually, the code contains the password at some point in time in a configuration file so that the system can access the database. And they had problems every time they changed the password. They'd change the password and they'd change it in the configuration file, and then a whole bunch of other things were broken. And so my friend found out that there were 7 different locations in this system, in the database, that were storing this particular password. And so that causes problems, right? When you change one place and it's duplicated other places, there's inconsistency and problems, and that shouldn't occur. Now, on the flip side, database management systems, or databases, try to maximize security. So we want to keep our data secure, and particularly we want to keep it confidential. That means that nobody can see it that shouldn't see it. Number 2, we want to maximize integrity. Okay, the data should be accurate. Okay, it should stay accurate. It shouldn't become corrupted over time. And number 3, this one's a little bit tricky to understand. The idea that we are trying to maximize data independence. All right. So this has really 2 parts to it. One of the parts is that if you need to change the data or access the data, you should go through the database management system. There should be no kind of back doors, which we'll talk about more later when we talk about security. But there should be no other way to access the data that doesn't go through the database software, okay, through the database management system. There's no way to change the data outside of that. And then number 2, related to the data independence, is if we change the underlying structure of the data, okay, meaning how the tables are related to one another, for example, it shouldn't impact our applications. Now, this is sometimes really tricky to do, but we should keep our program code and our database program code separate so that we can change one and not the other, or we can change one and the other won't break. Now, that's a hard thing to do, but it's important, and we try to maximize that. All right, so let's talk about this one. How are databases organized? Well, a database is made up of tables, and tables are made up of records and fields. Okay. Now the diagram shows that fields are kind of part of records, and they're kind of at the same level. But we should understand that databases are made up of many tables, one or many tables, and the tables are made up of records and fields. So let's look at an example of this. Here is a simple table in a database. Some of the same characters as before. So this table is made up of many records. Now, records correspond with rows, like in an Excel spreadsheet. We call them records when we're talking about a database. So this one has how many records? 6 records. And each of those records is made up of one or more fields. In this table, for example, there are 3 fields in this table: the ID field, the first field, and the last field. So here's a very important principle. Most of our databases now are called relational databases. The reason we call that is because we have multiple tables that are related to each other. And this is key. When we normalize things, we take them out of, for example, one big table, and we put them into multiple tables to remove the redundancy and to make things work. So I want you to do a little exercise. Without me explaining how this works, I want you to tell me what's the name, first and last name, of the customer that made the largest transaction. Let me pause the video and see if you can figure that out. All right, hopefully we were able to figure that out. Who made the largest transaction? Well, as it turns out, the answer is Daenerys Targaryen. Well, how would we figure that out if you couldn't figure it out? Okay, well, we would look on the right-hand side in the total column, and we would try to find the largest number, the maximum value. And that happens to be this $123.45 in transaction number 1. Well, if you look at the third field in the table on the right, customer ID is 005. And that customer ID corresponds to the customer ID for, on the left-hand side table, for Daenerys Targaryen. So we'll see this value right here corresponds to the customer ID 005, and that over here is customer ID, which links to this first and last name. And so customer ID field in this table links customer ID in that table, like so. In formal terms, we enable these relationships between tables by something called a key. And there's a couple, well, there's multiple, but for our purposes, we're going to talk about 2 of these type of keys. They're by far the most important. A primary key is one or more fields that uniquely identify a record. Here's an example. At the university, what is the primary key in some table in the registrar's office, for example, that uniquely identifies you at the university? Think about it. It's probably your student ID. Okay? So you have a student ID number that uniquely identifies you. No one else has that exact same student ID. If you are a U.S. citizen and you're paying taxes, what is the primary key in one of the IRS's tables about taxpayers? Well, in the U.S., that is your social security number, right? That's the primary key that identifies you, and no one else should have that same primary key. Okay? And so in these tables, we have customer ID is the primary key for the table on the left, all right? Customer ID uniquely identifies each of the records. So if I was to say, hey, customer ID 002, who does that identify? Well, it identifies Tyrion Lannister, okay? On the right-hand side, there's also a primary key. Transaction number is the primary key for this table. So if I was to say, transaction 005, it uniquely identifies this particular record, this transaction right here, okay? Now, foreign key. Foreign key is one or more field that uniquely identifies a record in another table. Let me explain what I mean by that. Customer ID right here on the right-hand table is the foreign key here, okay? You'll notice the customer ID is actually the primary key in the table on the left. It is put in the table on the right simply to link these tables together. So when you went and tried to map these tables together and found out that Daenerys Targaryen made the largest purchase, we might also be able to say, you know what? How many purchases did Daenerys Targaryen make? And we could look at, oh, here's her customer ID in the table on the left. And we could look in the table on the right, the foreign key field, and notice, oh, she made transaction 001 and also transaction 005. And actually, she made the largest 2 purchases in our database. And so the foreign key, which it isn't unique, look, it's duplicated in the table on the right. It's okay with that, but it uniquely identifies a record in another table, in this case where it's the primary key. All right, so how do we figure this out? If you're a database designer, one of the things that you do is you use data modeling, okay? So you go through a process where you come and try to figure out how the database should be structured. And this process of data modeling, we often use one type of diagram called an entity relationship diagram, or an ER diagram, sometimes called an ERD. In this class, I'll call it an ER diagram. ER diagrams are the standard. They were created a long time ago, 35, 36 years ago, and they've become, kind of the diagrams. And so we're going to learn some basics. I'm not gonna make you do much with ER diagrams. That's kind of the realm of the database specific class, but we're going to do enough to kind of understand what's going on. In the case that, what if a database designer came and talked to you about a system that needed to be built at your organization? Could you understand what they were talking about and help them to identify what the real world business problems are that needed to be represented in the database? So ER diagrams have their own terminology, and I apologize that these are called different things, but in ER diagrams this is what they're called, and so we're going to go by the standard notation. An entity in an ER diagram, the E, is a person, place, or thing that you want to store data about. It corresponds to a table in the database. So for example, maybe we store information about a customer, or about a transaction, or about a student, whatever we want to store information about. We want, a product, for example. That's what we're storing information about. An instance is a real example of an entity. So maybe an entity would be a student, sort of a conceptual name that is a collection of a whole bunch of records, whereas an instance is you, an actual student, and each of your classmates is an instance of the student entity. We'll go through some examples in a second. So here is a student entity represented by a kind of a rectangular box. And there are some attributes of this student. For example, the student has a student ID number, and a first name, and a last name, and an email. And in this diagram, you can kind of see that student ID is represented, and this happens to be the primary key for this entity. And we'll talk about how attributes are represented. An instance, though, of the student entity would be an actual student and the actual values. For student ID for this particular student, it's 4815, blah, 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 etc. And their first name is Walter, and their last name is White, okay? And their, email address is, this particular one, okay? So this is an instance of the student entity. All right, let's look at another example. Here is a section of a class. We'll talk more about this in a minute, but a section of a class has a section number that's its primary key. Your section has a section number that is its primary key. And it also has some other attributes, things like which building it's in, which room number it's in, what time does it start, what time does it end. And it also probably has a foreign key to the course. Okay, maybe it's the course ID, whatever this attribute ends up being called. And this is the entity and its attributes. Okay, but the instance would be the actual one. All right. So maybe the exact section number, and the exact building, and the exact room number, and the exact start time, end time, etc., and which course it actually is a foreign key to. And this is, not accurate this semester, but this is an instance of this particular section entity. Hopefully that's clear. An entity is a conceptual collection of people, places, or things. An instance is an actual one of those things. So let's talk about an ER diagram, how we would actually draw this out. So like I said, an entity corresponds to tables, and we represent entities in ER diagrams with rectangles. Attributes of a particular entity, in this case like the student ID, the first name, the last name, the email, all of those are attributes of the student. They're characteristics of some entity. In the database terms, we call these the fields. In an ER diagram, we call them attributes, and we represent them by these ovals or ellipses that have a line towards the entity. So, kind of this nice ellipse and a line towards the entity. Now, if the attribute corresponds to the primary key, if it uniquely identifies the entity or an instance of the entity, then we call that the identifier and put an underline under the name of it. You can see that there with student ID. So student ID is an attribute, but it is the identifier, the identifying attribute of this entity class. Now, what if we want to capture information about student registration? Well, again, we can put section in here. You'll notice I added another rectangle, which is the section entity, and some more ovals over here that have the attributes of the section. You should also notice that section number is underlined because that represents the identifier, which corresponds to the primary key of this entity. Now, how would we relate these together? Well, they do have a relationship together, and so we would model that by including this symbol. All right, so we would have a diamond, we'd give it a name. In this case, enrolls in is as good as others. I'm not as concerned about the name here, but this line and then diamond and line between these two entities signifies that they have a relationship with one another, that a student in database terms can enroll in a section. Okay, so in this diagram we have two entities, student and section. Each of them has 4 attributes. Each of them, one of those attributes on each of them is an identifier, and they have a relationship with one another. Okay, that's called enrolls in. Now, oftentimes we have business rules that help us to define how those relationships take place. And from database term, the thing that we care the most about is the maximum number of times that an instance of one entity can be related to an instance of another entity, and the minimum number of times that that can happen. We're going to go through an example of this, but we call this, the maximum we call the cardinality, and the minimum we call the modality, or sometimes the optionality. In this class we'll call it modality. Cardinality is a little more important than modality, but they're both important, and we're both represented on an ER diagram. So hopefully this is a little bit clearer. We'll go and talk about this in more detail. So let's say we have our entity right here. Okay, so we've got this nice entity with this rectangle. The symbol that is closest on the line, on the relationship line to the box, to the rectangle, is the cardinality. And we have two options. The cardinality can either be 1, all right, with this little single slash right here, or we can use this notation down below that looks like, well, we even call it a crow's foot, all right? So that little symbol right there, that represents many, okay? So cardinality can either be 1 or many. And on the right-hand side here, we again have either 1 or many, okay? Those are our two options for cardinality, the maximum amount. And we'll go into an example in a minute. Modality is the minimum number. And we really have two options here. We have either 1 as on the left side for modality, or we have a 0, okay, with a little circle on here. These ones are drawn very large, but they can be just a circle on the line here. Okay, so for cardinality, 1 or crow's foot, meaning many. For modality, which is the next symbol over, we have a 1 or a 0. Let's look through an example of this. Okay, we might change our mind on some of these. Let's think to ourselves, a particular student, let's say this student, you, okay, one student over here. How many sections can they enroll in? Well, many of you will enroll in multiple sections. Some of you will only enroll in one section. From a business rule perspective, for cardinality, do I want to have many or one as the maximum number of sections a particular student can enroll in? Well, we want to have students enrolled in many sections, all right? We want to graduate students. So this value, one student can enroll in many sections. That's how we read that. So that crow's foot notation right there, a student, one student over here on the student entity, can enroll in many sections. Let's do the other side. Let's say we have one section, this section of the class. How many students at a maximum can enroll in it? Well, this really depends on the room size and the maximum count on that. But we really only care for cardinality whether this is 1 or 0. So can more than one student enroll in this section? Well, the answer is yes. And so we're going to model that as a many, again, using the crow's foot notation. All right. Now, let's now move on to modality. We're talking about minimums now. So a student can enroll in a minimum of how many sections? Well, this is kind of a business decision. So in some organizations, can you be accepted as a student and enrolled in 0 sections yet? Yeah, that makes sense in some organizations. In other types of organizations, though, can you be a student until you sign up for a class? Well, in some organizations, the answer to that is no. And so we could, depending on the organization, put as the modality, put either a 0 or a 1, depending on the organization. So at Sac State, I believe you can be accepted without having enrolled in a section. And so our modality, one student enrolling in a minimum of how many sections, that would be a 0, and we'll draw a 0 right here. But again, that value could change from organization to organization. I think I have it the opposite way on the next slide. Let's go the other way. A particular section can have a minimum of how many students? Well, it probably makes sense for people, administrators, for example, to open up sections and to plan them ahead and have them in the system before any students enroll in them. Okay, when the registration time comes, students enroll in those sections, and that makes sense. So it probably makes sense to have this also have a modality of 0. So there can be a section that nobody enrolls in. Maybe they'll cancel that class, or maybe they just haven't opened it up for registration. And so that's how we would do modality and cardinality for this example. Now, because cardinality is actually the most important, sometimes when we're talking about relationships, we will talk about them in terms of their cardinality. So this also represents a many-to-many relationship. Let me discard. There we go. You can see that I modeled this one behind the scenes as a 1 here because in some organizations you aren't a student until you have enrolled in one section. But again, Sac State or other places we would probably put that as a 0. But we call this a many-to-many relationship. We use the name based off of the cardinality here. All right, now in class, next class, what we'll do is we will go and add the instructor entity to this diagram with a few attributes, pick 3 or 4, and the relationship along with the cardinality and modality. So what I want you to do for homework for next class is to see if you can figure that out. See if you can figure out how you would add an instructor entity to this diagram and how you would do the attributes, the identifier, and the cardinality and modality. So we'll do that next class. Additionally, the next class, we will also go and do another example for database design next class. If you want to get a head start on that, you can, but we're going to go and work through this. All right. Let's move on to a slightly different topic for now. We'll do more ER diagrams later. One of the important things about a database is our ability to add information to it and get information out of it, retrieve it, update things, remove things from the database where they're incorrect or where they're old and we don't need them anymore. And so in order to do that, we've developed, and by we I mean the industry has developed a standardized programming language for talking to databases, for giving them commands. And this standard language is called Structured Query Language, or SQL. So SQL is by far the most important database language. And we're not going to learn much in terms of SQL in this course, but you will be doing a very large project with a number of queries that SQL will be working for you behind the scenes. And we'll talk about that as we get closer to our database project. So you will be using SQL even if you're not aware of it. But here's a little example in the middle of your page. This is some SQL. Select star or asterisk from customer. So this SQL command tells the database, I want you to give me, select for me, everything, that's what the asterisk means, from a table called customer. So this query is telling the database, the database management software, give me everything out of the customer table. And that's what it would return, everything, all of the fields and all of the records out of the customer table. And we can do far more advanced SQL commands. And again, that's more of a topic for an advanced database class. All right, I promised we would get to data warehousing. Data warehousing, if you remember, is most commonly used for analytics and for data mining and for business intelligence, statistical analysis. What we tend to do is we take our databases, and our databases usually we organize based off of a specific function or a particular business unit or maybe an application that we have that comprises one database. And then we take that database and other databases and we move them into our data warehouse. So the data warehouse usually is a collection of information from a lot of different databases. But when we put it in there, we often will clean things and reconcile things. Maybe we have a database from our US operations and our European operations. Well, if that's the case, we would need to reconcile currency, for example, and make sure that when we analyze things, that things are in the same units, and that can become problematic. And so when we put things in the data warehouse, it's challenging to do so, but we put them in in a denormalized fashion so that they're ready for doing certain types of analysis. Now, sometimes people will use the term data mart as sort of a subset of the data in the data warehouse, sometimes focused around a functional area, something like that. It's not as common of a term, but you might come across it. But data warehouses are very important. As an example, when we denormalize our data and add back some redundancy for the purpose of doing faster statistical analysis, what we tend to use is something called a star schema. So a star schema, I don't know if it's really that much of a star, but that's what we've decided to call it, has one big table that has our main thing of interest that we care about. We call that the fact table. And then we also have other tables that are related to that particular fact, okay? And so our fact table in this case has information on the employee, the customer ID, the product, the calendar, the sales order number, the order quantity, and the unit price. So really some information about the transaction. That's the most important thing in this particular data warehouse. So related to that, we have other dimension tables. These are sort of the arrows of the star. Have information about the region and the more information about the employee and the product and the customer. But this type of format is much, much better for data analysis, even if it does have some redundancy. So data warehouses tend to be large because they have multiple databases and large because they have some redundancy built in. but that's okay because they're better for analysis. So here's a mini case that's an interesting organization. Health Catalyst is one of the leading, it probably competes with IBM as the leading provider of healthcare data warehousing. So they're a large growing company. They've taken in many millions of dollars in venture capital money, and in this region they provide data warehousing for Kaiser, for example, and for Stanford University hospitals, and their goal is to take that information and do some analysis and allow the healthcare organization to better get information and analytical results on patient outcomes and operational costs, and answer questions like, what is the riskiest procedure at our hospitals? What is the most costly procedure at our hospitals? How long between onset of one particular condition to an average onset of another particular condition? We'll talk a little bit more about this when we talk about analytics. But this is an interesting organization that's doing this in the healthcare space, which is a hot area right now. All right, so like I said, next class, we're going to do a review for our exam, and we're also going to talk about some of the ER diagram things, and we're going to answer any questions that you have. So come with your questions, both on databases, but also on any of the topics we've covered so far. It will be mostly driven by you, and a few things on data warehouse or ER diagrams. And then after our exam, we will then start talking about data communication. And so please make sure that you do the readings and do the questions about data communication. That will be after our exam. All right, thanks.